Introduction. Capacitors are essential components in electronics because they store and release electrical energy. In many applications, they continuously charge and discharge, such as in signal filtering and energy regulation. In a simple RC circuit, this process happens quickly and at first and then slows down over the time. Specifically, it's the time required for the capacitor to reach about 63% of its maximum charge. This experiment will study the process to better understand the relationship between resistance, capacitance, and time.
So for the materials, we will start with Pascal 850 Universal Interface, which is a signal generator, and at the same time, everything in this experiment connects to this interface and projects the results on the computer which it is connected. The next is Passport voltage/current sensor, and as the name suggests, it measures both voltage and current at the same time and sends these informations to 850 interface. The next is negative and positive voltage sensor, and the red one, which is connected to the positive on the signal generator, sensors the positive voltages, and the black one is connected to the negative, and it senses the negative voltages. The last one on the bottom with blue and everything like the wires are connected on there is called a circuit tablet, and I'll explain that on the next slide. So the circuit tablet has resistors and capacitors on it, and they can generate different resistances and capacitances, which we will be using to compare with the experimental capacitance. And the theoretical capacitances that we're going to be using to compare with the experimental is already on the circuit board, and it's on the very, very right, and these small and blue ones, in which is in 100 microfarad and 330 microfarad.
Before the experiment can begin, we must adjust the conditions for recording on Capstone to the following settings. In the top right corner, you can see the interface for where the settings should be adjusted, and in the bottom you can see what it looks like and how to navigate to those settings. So what we must do is set the frequency to 1 Hz, the phase shift to 0, the duty cycle to 50, the amplitude to 5 volts, the DC voltage to 0, the voltage limit to 10 volts, the current limit to 1.1 amps, check positive for auto, waveform set to positive square, and the voltage current sensor to 250 Hz. For part 1 of the experiment, we connect the series circuit with the signal generator following the diagram to the right. This is the setup that will be used to collect the data for Table 1 on the following slide. The same procedure for collecting the data is used for Table 2, however, the setup is slightly different and 2 of the capacitors are connected in parallel and then connected in series to the resistor, whereas in the first part of the experiment there was only one of each. As I stated in the previous slide, the procedure for tables 1 and table 2 are pretty much the same, except they have different setups on the circuit. How this is done is by clicking record on the Capstone software and then letting it stop the experiment. Then you would zoom into one instance of charging and discharging the capacitor and then use the add coordinates function at the time where the voltage would be 0 and when the voltage is at 63% of the total voltage. Then you would subtract those two values T2 minus T1 to find T, and then use these variables to solve for the theoretical capacitance. And then, of course, your experimental capacitance would be given by capstone. The video on the left shows what it actually looks like when capstone is running the experiment. This was explained in the previous slide. I just could not fit all the pictures and videos into one slide. Then on the right, on the top, we have the experimental data from table 1 with the first circuit setup. Then on the bottom of that, on the bottom right, is the experimental data from the second setup with the altered circuit. These values are later expanded upon in the data and analysis section.
This is data and data analysis for lab report 6. Once we finished with our procedure or setting up the capstone software, we were able to record our first graph as was shown in the previous video. Once we were able to record our first graph, we did zoom into it so that way we could locate one specific area. Before, this is a picture or a screenshot of what it looked like, our first graph. So for our voltage, it was 0. And then voltage is on our Y axis, and then on our X axis is time. So while voltage was 0, our first value was 0.498. And then while voltage was the 63% of the total voltage, which is 3.15, our time was 0.503. So this is lab 6, table 1, which is our experimental values for one capacitor. Again, from our graph and using the point system, we were able to see our voltage 0. Our time was 0.498. When our voltage was at 63%, which is 3.15, our time was at 0.503. From there, we found our experimental time constant, which is our T2 minus our T1. And then for that value, we got 0.005. Following that, we found our experimental capacitance, which was that same number, the 0.005, divided by the 33 farad. And then from there, we got our capacitance of 0.000151. And then our theoretical, we had gotten it from it being 100 microfarads. And then we changed it into normal farads, which was 100 to the negative 6 power farads. And then for our experimental error we found it using theoretical minus our experimental divided by our theoretical times 100. So for our percent error for our step 1, we did get it at 51%. And then this is our step 2. For our step 2, we connected both capacitors in parallel and then in series with one of the resistors. With the voltage sensor across the junction of the capacitors, we were able to create a graph again, and then we zoomed in so that way we could add the points, so that way we could use that to find and complete our table. So for our second graph, our voltage at 0, our time was 0.498. So it was at the same time as our beginning or our first step 1. And then for our voltage at 65%, which is 3.15, our time was 0.517. So there was a slight difference, but they were very similar either way. And then this is a screenshot of that graph. So this is our step 2 table. Our table 2, which is the experimental values for 2 capacitors in parallel. Of course, for step 2, we did connect both capacitors in parallel and then in series with one of the resistors. With the voltage sensor across the junction of the capacitors, we were able to plot the points again and then get our information. So for voltage at 0, our time was 0.498. For our voltage at 63%, which is voltage 3.15. Our time was 0.517. And then from there, we use the same formula of T2 minus T1 to equal the experimental time constant. For this value, for this, our second step, we got 0.019. Using our time constant, we divided it by the 33 farads to get the experimental capacitance of 5.75 to the power of negative 4. For our theoretical capacitance, since our step 2 was connected with both capacitors in parallel, our theoretical capacitance would be equivalent to both, or the sum of both capacitors. And then that was 4.3 to the power of negative 4 farads. Using those two values, we were able to find a percent error, which again is our theoretical minus experimental divided by theoretical times 100. And so for our percent error for this, our second and final step, it was 33.7%.
Turning to our experimental findings, for the single capacitor circuit, we measured a time constant of 5 milliseconds. Using our circuit resistance, this resulted in an experimental capacitance of 151 microfarads. When we moved to the parallel configuration, the time constant increased significantly to 19 milliseconds, yielding a total capacitance of 575 microfarads. This clearly demonstrates the additive nature of capacitors in parallel, fulfilling our primary objective from Lab 6. While the trend is correct, we observed a 51% error in the single trial and a 33.7% error in the parallel trial. This is a classic case of sampling rate limitation. The Pascal system was set to 500 Hz, meaning it only checked the voltage every 2 milliseconds. In a 5 millisecond event, missing the exact 63% mark by just one sample creates a massive percentage jump. However, as the time constant increased in our parallel test, the error dropped, proving that a slower charging cycle allows for a more precise data capture. In summary, our presentation confirms that while equipment limitations impacted our precision, the fundamental physics are verified. The relationship between resistance, capacitance, and time is consistent. To improve future results, we recommend increasing circuit resistance to 100 to provide a longer measurement window. This concludes our report on RC circuit dynamics.